Hello everyone, good afternoon. My name is Rajan Kumar and I am from Meta. I work in networking infrastructure FBOSS team at Meta, and I am going to present FBOSS experience of migrating our software to SAI. So I have my colleague Sri Krishna, he is online, and first I will show his video, then I will talk about the other part of the presentation.
Hi, I'm Sri Krishna. My co-presenter is Rajan. We are software engineers at Facebook and we would be presenting FBOSS experience on migrating massive scale networking systems to SAI. FBOSS stands for Facebook Open Switching System. FBOSS is Facebook's software stack for controlling and managing network switches deployed in Facebook's data centers. Let's talk about FBOSS architecture. The software switch is the hardware independent part of FBOSS, while hardware switch implements the hardware specific logic. It is possible to plug different implementations for hardware switch. One such implementation is BCM switch. It uses vendor API to program the ASIC, while the new SAI switch implementation uses the open source SAI API. We will talk more about SAI in our next slides. SAI stands for Switch Abstraction Interface. It is a project under OCP. It defines open source API to control forwarding elements. It's a vendor independent API. FBOSS now has SAI based implementation. It allows us to have single hardware switch implementation for multiple ASICs or ASIC vendors, which means it's easy to onboard new ASICs. Also, it further enables us to make open source contributions. FBOSS is already in open source, and Facebook contributes to the open source SAI spec as well. We have deployed the non-SAI implementation in production at massive scale across a variety of ASICs, roles, and features. The challenge was, how do we develop and safely migrate from non-SAI to SAI implementation? Here is the strategy that we used. We identified the combination of ASICs, roles, and features actually deployed in production. We then identified that rack switches have larger deployments but relatively fewer features. Thus, we developed SAI implementation for rack switches first and started deploying it while developing SAI implementation for other switch roles in parallel. Here is the development model that we followed. FBOSS SAI support meant that we had to implement a new hardware switch implementation. We developed hardware tests. In this case, these tests validate one aspect of functionality used in production. These tests are hardware switch independent and thus can validate any hardware switch implementation. The passing criteria for FBOSS SAI implementation is, if a test passes on non-SAI, it must pass on SAI. We built extensive coverage with hardware tests for each of our features, so we have over 500 hardware tests. Our development was in close collaboration with Broadcom. We use Broadcom's SAI implementation. At times, features were developed in parallel by FBOSS and Broadcom. Broadcom gave us periodic early access drops and a GA release when we were feature complete. Facebook contributed several patches to Broadcom's SAI implementation as well. As needed, we would have joint debug calls with Broadcom to debug and integrate these two solutions together. One of the tools that helped debugging was what we call a SAI replayer. When a hardware test is run, SAI replayer is a tool that will auto-generate a log of SAI API calls. The log is actually a C code that uses all the SAI APIs, and one could compile this C code and run to recreate the ASIC state without having to run the hardware test. This is a massive scale brownfield deployment. That is, we have to convert existing fleet of production devices from non-SAI to SAI based implementation. For FBOSS, push is a continuous process that updates FBOSS software running on every device in the fleet using a qualified bundle. A bundle is qualified using a series of checks, hardware tests, canaries, that is going from current prod image to image we want to qualify. Once qualified, the new image is gradually pushed out to all the devices in the fleet. FBOSS non-SAI binaries on all the devices in the fleet were getting upgraded using this process already. We had to enhance this workflow for SAI conversions. We built a parallel qualification pipeline for qualifying FBOSS SAI implementation, that is hardware test and canaries for SAI. Then each push now did following. For non-SAI binaries, same as before, upgrade non-SAI binaries using the qualified bundle. For SAI devices, upgrade SAI binaries to newer version of SAI binary using the qualified SAI bundle. Additionally, the push would also schedule conversions to convert non-SAI devices to SAI devices. Note that these conversions are disruptive to traffic, so require draining the device, and thus they tend to be slower than the usual upgrade. With each subsequent push, we continued to extend the number of devices we wanted to schedule new conversions for as part of that push. Note that some subtle bugs can only be found in production despite the large test suite that we have. We can categorize the issues and challenges into these buckets: vendor SAI implementation, FBOSS SAI implementation, push tooling, ability to drain devices as upgrades from non-SAI to SAI are disruptive to traffic. We could only drain devices at certain rate because draining takes away production capacity. So that limits how quickly we can convert devices to SAI. Here are some examples. Vendor SAI implementation had an implicitly created security ACL that dropped packets when source MAC equaled router MAC and the packet was ingress on a front panel port. We had one production service that was sending such a traffic, and that worked fine with non-SAI implementation because it did not have this ACL, but the moment we converted from non-SAI to SAI, we hit an issue in production because such packets started getting dropped. Then there were some other issues like some incorrect route programming or some of the races which were only apparent when we started deploying in production. Some examples of issues that we hit in production around FBOSS implementation. We were programming ACL counters correctly, but we were not exporting those to our monitoring dashboards. For queue watermark stats, those were created for some queues but not for all queues. Then there were some link flaps on certain ports of some rack types, and we had some issues around route being incorrectly programmed to CPU instead of front panel port. In terms of mitigation, when we encountered an issue, we would pause the SAI conversions, root cause, have a fix, and then resume. Sometimes, depending on the issue and its root cause, we would pause the conversions only for affected ASIC or switch role, but continue to deploy to the rest of the fleet. On resumption, the devices that would get newly converted from non-SAI to SAI, those were fine because they came up with the fix. But at times we needed to add additional logic because there were already devices running SAI with the buggy version in the fleet, and we had to warm boot from that version to with fixed version and recover. By warm boot, I mean we want to upgrade the binary from buggy version to fixed version without any traffic disruption. We also have a feedback loop where, to prevent recurrence of an issue, we would enhance our hardware tests. And these tests run on diff as well as on a continuous runs. And as we saw earlier, they are used to qualify a new bundle, which means that any recurrence of issue gets caught pretty early in the process. This was one interesting case where we hit a bug in production where traffic to certain route will get dropped. The bug occurred extremely rarely, and a warm boot would make the issue go away. This was very difficult to reproduce despite several attempts, and thus it was very difficult to debug and root cause. Here is the technique we used. We added extensive targeted debug logging to point to the root cause in case there is recurrence. We also added pre-untrained checks because the SAI conversions from non-SAI to SAI, they are disruptive. So the device is out of production at that time. So we added checks that will check if the issue recurs, and if it does, it would not return the device to production, but leave it for us to debug and not harm production in any way. Moreover, we added continuous monitoring on all devices in the fleet so that in case there is a recurrence on a device already running SAI, then that would get logged, and we also tied that with automated remediation. So that way the device will recover, not cause any production issues, and the log will tell us where the recurrence occurred so that we can go and investigate it further. All put together, it allowed us to make safe progress without affecting production, and thanks to the logging and all the monitoring checks we had put in place, when the issue recurred next time, we were able to use those logs to root cause. It turned out to be a very rare race in the code, which we have since fixed. With that, let me turn over to my co-presenter Rajan for the rest of the talk.
Hey, thanks, Sri. Okay, so in the previous video, Sri talked about the NPU aspect of the SAI, and I am going to talk about the PHY aspect of the SAI. So as some previous presenter from Meta has also pointed out that we are deploying various switches at different layers. We have a multi-tier deployments. So many of these switches use the PHY. So we use the internal and external PHY depending on what kind of deployment it is. So by internal PHY, I mean that the PHY functionality is integrated inside the switching ASIC itself, like for example, the Tomahawk 4 or any other ASIC. And the external PHYs are the PHY which are like sitting as a separate device on the board. So we use both kind of PHYs in different products. And these PHYs are managed by vendor provided SDK, and some of the PHYs we are managing by our own homegrown SDK. So we have got mix of that. And we have got multiple PHYs, so because there are too many switches sitting at different layers. So what we needed was that from the software point of view, we wanted to have a standard interface, a standard software interface through which we can program all the PHY in a unique way. Because earlier what was happening was that different vendor will provide their own SDK, and they will use different kind of APIs to program the PHY, program a port, program lane. So there is no commonality between the APIs. So we thought of coming to a standard and adopt the SAI in that aspect. So we integrated the SAI for the PHY device as well. So the way we did was, first we isolated all the PHY management related code, and we moved all the PHY management related code into a separate process. And then we identified all the PHY management, PHY related function calls, and we channelized all of them through the SAI layer. So we integrated the SAI based device driver, and then we started calling the SAI functions. And some of the functions that we are using SAI to do the PHY work is like something like PHY initialization, PHY firmware download, port and lane setting. Then there are multiple counters and flags, and recently the feature like MaxSec we are implementing through the PHY. So and our PHY management code not just directly talk to the SAI layer. We have got a homegrown SAI adaptation layer. We call it SAI switch. So in the next slide, I will talk about the advantage of using that SAI switch. So our PHY management code talks to the SAI switch, and SAI switch talks to the SAI-based SDK, which is provided by the vendor, and that SDK is managing the PHY. Yeah. So when we move to the SAI for the PHY related functionality, so we got several advantages. One advantage is that now we have got a common interface to manage all the PHY. So we have got different kind of PHY coming from different vendor. So we can have a common interface to manage all of them. And since our PHY management code is calling similar APIs, similar SAI API, so it becomes easier for us to migrate from one vendor to another vendor, provided the vendor is providing the SAI SDK, SAI-based SDK. And we have got the integration with our homegrown SAI adaptation layer, which we call SAI switch. This is also open source code. And the advantage of using SAI switch on top of a standard SAI SDK is that SAI switch has got several advantages over SAI. First of all, the SAI is itself like it's a C-based code, and there is no strong type checking. So in the SAI switch, there is a strong type checking. So we cannot send wrong parameter to SAI layer. Then we have got the features like warm boot. We record all the states whenever APIs are called, and then that helps in doing the warm boot. And then we have got something called SAI API logger and API replayer. So if some problem comes, then we can dump the list of all the API that were called prior to the issue occurring, and then we can send it to vendor so that they can debug the problem. So these are the features for which we are using the SAI switch, and it has been very helpful. And this is the same SAI switch which is used for the NPU SAI also, the part of the FBOSS code which is managing the switching ASIC like Tomahawk 4. And with this, we are able to align our FBOSS code such that all the ASIC are getting managed by the SAI code, managed through the SAI-based drivers. We not only get the advantage during the development when we use SAI, we also get the advantage of testing. So we have got elaborate testing infrastructure. One infrastructure is that we have something called hardware test. So in the hardware test, we are able to, since now we are calling the SAI code for the PHY functionality, so we are able to use this hardware test infrastructure to test the PHY also. And this hardware test infrastructure has got multiple tests which were earlier built to test the NPU functionality. Now we have extended it to test the PHY functionality also. And recently we have also extended to support the MACsec testing. We have another testing infrastructure called unit test infrastructure, and the unit test infrastructure, it runs on the dev server itself. It doesn't work on the hardware. So it uses something called fake SAI. Fake SAI is something like an emulation of SAI APIs that we have developed for running the quick test. So since we migrated PHY management to the SAI, so we are able to leverage this unit test infrastructure also, and now we are able to add multiple tests to test out the PHY code. So there are challenges when we move the PHY functionality to the SAI. These are the challenges we face. There are not many PHY vendors who are providing SAI-based SDK. That is the number one challenge. So we are talking to the PHY vendors, and we are encouraging them to provide us the SAI-based SDK, and we are getting positive response. So yeah, we have migrated some of them. And now, since not every vendor is providing SAI-based SDK, so in our code, we have to maintain two support. The support for SAI-based SDK and non-SAI-based SDK. That is why for some time we will have to continue maintaining these two support. And another challenge we face is that although SAI is quite mature for the NPU related work, but it is still evolving for the PHY functionality. There are many gaps. There are many features like lane level settings are not there, or many debugging flags, counters, they are not there specific to the PHY. So for that, we are working with the vendor, we are working with the community to identify the gap and push those attributes, push new APIs in the SAI spec. Yeah, and another challenge that we have faced is that now we have got a SAI switch layer, which is talking to the NPU-based SAI as well as the PHY-based SAI. It is talking to different kind of SAI, and these SAI-based SDK are implemented by different vendors. There are, although SAI completely specifies that, okay, this API has to work in this way and return this error code, but still there are some small confusions. Like, for example, there are some confusions around the return code of the SAI code from the SAI API. For example, not valid, not supported, invalid API, invalid argument. So there are some confusions around that. So some vendor report one kind of error in those conditions, some vendor report another kind of error in those conditions. So what happens is that in our SAI switch layer, we have to take care of different conditions. So that is another challenge that we have faced. So whenever we encounter this kind of problem, we talk to the vendor and get the error code fixed. So this is what we are planning to do. We are going to move all our existing FI SDK to the SAI-based SDK. So there are some vendor-provided SDK which are not in SAI header-based. So we are talking to them. We are getting them also moved to the SAI. And we have some homegrown SDK also. So we are also exploring the option so that we can make them SAI-based, put the SAI support on top of it. And we are trying to strengthen the SAI API for FI functionality. We are identifying what all gaps are there, and we are talking to the vendors so that they can implement those attributes, those flags, counters, so that it becomes better. And there are a lot of things were missing when we started to work. We identified like port level counters, lane status flags, all these things were missing. So we have talked to one vendor and got many things implemented. And we are also trying to come up with, trying to encourage vendors to come up with some kind of software simulation model that will help us in the unit test infrastructure. So right now, our unit test infrastructure uses something called fake SAI. Fake SAI is something like whenever our FI management calls on SAI API will do some dummy calls. So apart from, instead of that, what we want is the FI vendor should provide us the software emulation, the functional accurate emulation model for their FI, so that we can just plug it into our SAI code, and the whole thing will run on the dev server itself, and it will emulate the FI. That will test out our FI management code in a better way. And this is call to action. Like, we will work with the community just to streamline some of the process and add some missing piece of the functionality. So on the process side, what we have found is that earlier, we found a couple of instances where a new SAI version was released, and that broke the warm boot support because new enum values were introduced, which conflicted with the previous one also. So we can work with the community and streamline the process. We can add some test cases which will prove that, okay, this is not going to break the warm boot support or any other support. And similarly, there were some concerns regarding spec enhancement, faster turnaround related concerns were there. So we can work with the community and try to come up with the process to get the new spec turnaround fast. And as I said that there are some counters, flags, many things missing from the FI side. So we will work with community and identify the gaps and push all these new attributes, new APIs that has to be supported by the SAI. There are many things we found that on the debug side, it was missing, like signal to noise ratio, bit error rate, eye diagram. Those are very useful things for debugging the FI functionality. So those things were missing. So we have identified them. We are in the process of identifying more, and then we'll work with community and get everything committed in the new spec. So yeah, so that's all about my presentation. So thank you, and let me know if there is any question.
Great. Okay, one quick question here.
Yeah, I have a question. This is Jay from Broadcom. So I just wanted to clarify, you talked about the warm boot. So enum numbering, we have already taken care of it. That as tool chaining has been fixed. And anytime you do the SAI update on any header file, you have to follow certain rules. And if you don't, then the tool chain will forfeit you. So that's already taken care of.
Oh, that's great. Yeah, see, that's the power of community.
Yeah, maybe one last question here. Yeah.
So, your test cases, do you have them available in a publicly available form that can be used in other frameworks?
Our NPU-related test cases are available, but the FI-related test cases are not available yet. So we are still developing those test cases, and in future we will make them open source.
It's my understanding that your framework itself is still closed. So how do your test cases, how can they be consumed by other people in other frameworks?
Okay. Yeah.
Okay.
So, in the GitHub FBOSS repo, the tests are open source, so there are instructions to build and compile them with your favorite SAI implementation. So it's really G-test, so you don't doesn't really depend on a larger framework to run them, but our automation CI/CD pipeline has a different framework to engage them, but you can run them just as G-tests.
Thanks a bunch, and please help me thank the speakers.
Thank you.